pleasure to speak here. Thank you for the organizers. It's a little intimidating to be talking after two musicians. I'm not a musician. My only excuse to present this is that other than the fact that I love music, is that there is a large body of literature written by physicists mostly and mathematicians on fractals in music. And there's lots of disputes about it and what does it really mean, and comparisons between different methods and so on. And my involvement in this came about because we had a student at Boston College who was a physics major and mathematics major. And he came to my office one day and said, I'd like to write a senior thesis, which is something we have. There is an option for students and that combines my two majors. Can you invent something? And with a delay of about 1 second, I said, sure, let's do something on fractals because I really want to understand what people mean when they do this. Okay, so that's how this came about. And we've published this last year. And so first of all, this is my collaborator who's now a graduate student at Boston University. And we're starting to work on a sequel. I've consulted with lots of musicians to partly ameliorate the fact that I'm not a musician myself. So here are some names. The first three, Peter Phillips, Stephen Lipsitz, and Alyssa Wang, are all conductors. The first one of the very well-known Tallis Scholars Group, and then two Boston-based orchestra, and then one is a professor of music at Boston College. So when we first started to work on it, I knew basically of one kind of fractal pattern, which had no name, and we called it nested sequences. So I want to say a word about this, especially that it's a segue to the real, or at least in my view, real fractal pattern in music, which are prolation canons. And here in this image, you see Johannes Occam, who invented this method and wrote first examples. And then I want to talk about temporal dimension. I'll explain what I mean by this, tonal complexity, and then put these things together for what we term fractal dimension, and give some examples spanning about 500 years. We have many more examples that I can put into this talk, obviously. But nevertheless, I should say right at the outset that this is a rare thing. It's there throughout history of music. Prolation canons were very popular, relatively speaking, in early Renaissance, but they are now again popular with modern composers. Arvo Pärt, for example, whom I'm not going to illustrate here, and many others. And I've gotten one living composer in Boston area interested in writing a prolation canon. Okay, and I'll make some remarks at the end. So first, just an extremely brief look at what other people do, because what we did is perpendicular to what other people do. And basically, since these are physicists, and since they're facing a time series of certain kind, they try to apply various statistical approaches to analyze this time series. So I'll just flash this very briefly, some of the most common approaches. Remember, this is in physics literature, not in music theoretical literature. So the beginning of this is this paper from '78 on sort of 1/f power spectra. So basically this is a power spectrum plot taking all the notes in what the authors claim is classical, jazz, rock, and other things. And basically they get the same thing. So it doesn't discriminate between different kinds of music or noise. It's really sort of serves no real purpose. And of course also has really nothing to do with fractal dimension. But that was the beginning. Much later, people use fluctuation analysis and detrended fluctuation analysis. It basically, very, very briefly, it consists of designing little time windows, and within time windows of different lengths and covering the whole compositions, they measure deviation from the average, and then there's some special method to eliminate some spurious effects. It's called, that's why detrended. In any case, on the log-log plot, where on the horizontal axis there's a log of the lengths of the time window, you get these quasi straight lines, and people make some inferences about the styles, etc. The slope of these lines is Hurst exponent, one of the many exponents that one can measure for time series. And there is a variant of this called autocorrelation of normalized averages. I'm just going to skip this. And there's one more method used by quite a few authors, and that is basically plot some property of music, for example, loudness, versus time, and then treat the plot itself as a fractal structure and try to find out what the dimension of this may be. The least promising, I think, of all these methods. So as you can hear from the way I speak about it, I'm not tremendously impressed by some of these methods, and here are some of the reasons. So first of all of these analyses focus on one aspect of music. It's very often loudness. And loudness, you know, one performance of Ninth Symphony is going to have different loudness than another performance. What does this even mean? There's some pitch frequency, that's good. Some pitch intervals from one note to another. That's pretty much it. But the most important thing is they take one characteristic, right? And I note here that music depends on all of these things. If you took, since it was given as an example several times, Ninth Symphony and wrote every single note at the same value, the same length, it wouldn't sound like Ninth Symphony anymore. So it's very important to have take into consideration not just the pitches, but also the lengths of the notes. So yeah, you can get various statistical parameters such as exponent, Hurst exponent, and so on. And it is true that for real mathematical fractals, it's related to fractal dimension. But it only happens at exact self-similar patterns. And almost all of these examples that are analyzed in literature, of course, are not self-similar patterns. And Ninth Symphony is hardly an example of a self-similar pattern. So there's some disconnect. More importantly, perhaps, H is a global measure. So very typical for papers on this topic in physics literature, you will see the whole entire piece by Palestrina or the whole entire piece by I don't know, Vivaldi, which of course changes all the time, has different movements, changes within the movements. There are little passages of different character, and so on. So if it measures anything, this H for music, it measures some global property. Whereas fractal dimension describes what happens at small scale. It describes a fine structure, right? You zoom into smaller scales, and if you see the same pattern, then maybe this is a fractal pattern. All these methods, statistical methods, depend on averages, of course. That's what statistical things are. And even more troubling, with few exceptions, are insensitive to the order of notes. So imagine you take, I don't know, the third movement of the Beethoven's 9 that we've heard, and you randomly redistribute the notes, you're gonna get nonsense. But you're gonna get exactly the same analysis using these statistical methods. So they miss a great deal, to put it mildly. So music really depends, as the previous two talks illustrated amply, depends on precise sequence of notes and cannot be understood in average sense. And finally, in some sense, these time windows are analogs of boxes in typical fractal analysis of images. But there is a cognitive disconnect for the following reason in using it in this way. Namely, when you look at image, fractal or otherwise, you see it and all the scales in it all at once. But you don't hear all the time windows in music all at once. You only hear one instance, and you understand music by remembering some selected passages from earlier times. You certainly don't understand music by hearing an instant and then comparing it to what you're going to hear later on. That's very difficult to do unless you've heard the piece many times. So we think that these methods miss a lot. Do they measure something? Yeah, they measure something, but maybe not fractal dimension. So our idea is, as I just emphasized, music cannot be perceived or analyzed in averages. You need to zero in on fine scale, by which I mean on melodic motifs that were talked about. Dimitri talked about them quite a bit. And you can't look at just one thing. You have to look at the tonal contours, so basically the melody, and note duration, so the rhythm. Both of these things have to be included if you want to have any chance of characterizing music in a accurate way. And now for some analogies. Visual fractals depend on scaling regularities in space, in an image. So musical fractals must depend on scaling regularities in time. Dimitri mentioned, I was very pleased, fractal patterns briefly in passing with exactly this understanding a moment ago. So I'm happy about this. This is how I understand things as well. Self-similarity in an image implies appearance of the same pattern at various spatial scales in the same location. You zoom in and you see the same pattern, for example, in Sierpinski triangle that was discussed just a second ago. So self-similarity in music must imply appearance of the same pattern at various temporal scales, meaning at the same time. Same location is analogous to same time. So various temporal scales means at various speeds. So scaled up, down visual patterns in images correspond to music motifs slowed down. That's called augmentation. Or sped up, diminutions in music. And now a caveat of my own is that, of course, you can't expect in music infinite number of scales. In some examples that we've analyzed, there's only 2. So these are really not fractals in mathematical strict sense. That's why we call them patterns, fractal patterns. I know of a piece with 5 orders. I'm not going to mention it here by Britain, but I haven't seen one with 6 orders. There's a good reason for this, which is that especially in prolation canons, and I'll explain in a moment what that is, already having 3 scales is enormously difficult. It's a feat, mathematical and musical achievement. 5 orders is almost impossible to do. I'll explain in a second why that is so. And of course, in music, you can't expect exact repeat of motifs. And furthermore, you've heard in the last 2 talks a lot about transposed, right? So the motifs can be transposed. That means moved up or down on a staff, with all the notes retaining their relationship. They can be inverted, that was mentioned by Dmitry. That means basically mirror flipped via horizontal axis on the staff. And there can be in retrograde. I was surprised nobody mentioned retrograde. Retrograde means played from the back, so last note first and so on. There are compositions in this world that can be played both ways, from the beginning to the end and from the end to the beginning, most famously the Bach's Crab canon, but others as well. Now you've seen a lot of notations here, so maybe I'll be thrown out of this room by saying this, but I just want to remind everybody, including people who are not musicians, that we use now equal temperament scales, which means that the frequencies of the consecutive notes have the same ratio. It's given perfectly by root 12 of 2. And these notations here correspond to the values or lengths of the notes, which I mentioned are very important. Okay, good. So let's start with nested sequences. So this idea came from a paper in '93 by Henderson, Sellers, and Cooper. So I call it HSC for short. And they proposed what a fractal structure may look like by just writing it down. And this is what they wrote. So they wrote 4 full notes. That's the first order of the fractal structure. Think of creating, for example, Sierpinski triangle or some other mathematical fractal 1 order at a time. And then each of these full notes is replaced by 4 quarter notes in such a way that the leading note of each quartet is of the same pitch as the corresponding note above. I forgot to get the, I don't know if there's a laser pointer here, but in any case, I think you can see what I mean by this. And then, in the next order, order 3, every quarter note is replaced by 16th note, again, starting at the same frequency, same pitch, as the note corresponding to it above. So we've written this in such a way that you can see how these things align. So this is what it sounds like. So notes about this are this. Here, different orders are not simultaneous in a literal sense. They are simultaneous implicitly in that each order contains in the leading notes of the repeats the memory of the previous order. So each order contains the previous order. In that sense, it's simultaneous. And here, this is a very simple example where all the notes at every order have the same duration. And look, the usual definition of dimension is number of copies. So number of copies at each order is 4. And the log of that divided by log inverse scale. The scale is 1/4. So it's log 4 over log 4. That's 1. So dimension would be 1 if anything. So this kind of example is Euclidean. It's integer dimension.
Sorry, what were M and S there?
M, number of copies.
Okay.
So from one note I get 4. From one note in the second order I get 4. So number of copies divided by inverse scale. Scale is 1/4 from full to 1/4 to 16 note. And so it's like this. Okay, so it's inescapably Euclidean integer dimension. So the first thing we did is we extended this to non-Euclidean examples of these. And you can see why we call it nested sequences. These notes are nested within the notes of the previous order. So I set out to use two common examples in addition to Sierpinski triangle, which was mentioned. So the Cantor set, as you know, is, sorry, it started in the middle here, but it will come full circle in a second. You take an interval, you divide it into 3 parts. You remove, maybe, is it going to come back? It doesn't want to come back. Oh, there. You remove the middle part. From the remaining 2 parts, you remove the middle part, and so on, right? That was invented by Gregor Cantor when he was thinking about definition of real numbers. So in this case, you have 2 copies of the original in each order. The scale is 1/3. So you get something that has a dimension about 0.63. And then the sort of flip example is Koch Curve. There are many variants, but for my purposes, you start with the interval, you make 4 and a little hat like this, and on each side you repeat the procedure ad infinitum. In this case, you make 4 copies at each stage. The scale is still 3, so log 4 over log 3, 1.3 roughly. Okay, so here is the musical Cantor set. I have to say that in music, dividing into thirds is very difficult. It's doable, but it's difficult. It's much easier to divide into halves, quarters, and so on for obvious reasons. So we did a version that we have here. So we have a middle part that was removed, you can see, is 2 rests, and then each note is replaced by 2 with a rest between them and so on. And here's what it sounds. Not very interesting, very sparse. Dimension is 1/2. That's what it is. Here is the musical Koch curve. We start with a little hat, and then each note is replaced by 3, etc. So a full note by a half note, by a quarter note. So the dimension is about 1.6 in this case. Okay. So much for nested sequences. Now for real thing, or at least what we claim as the real thing. So in a real fractal pattern in music, you would have different scales, different tempi simultaneously, truly simultaneously. So basically, this form is a canon where each voice performs the same melody but at different speed. Right? As I said, this was invented by Occam. There is the first known example is Missa Prolationum, which was written at the very end of 15th century, but it exists in manuscript from 1503. So before I dive into this, a brief note on regular canon. Regular canon is a situation, this is the most famous of them all, Frère Jacques, where you have exactly the same melody, but the melody is interacting with different parts of itself by virtue of different voices starting at different times. So here, two measures after the beginning line is the second line, 4 measures is the third, and the effect, I think you know. The voices drop one by one. So it's not easy to write a canon like this because it needs to sound well when the melody interacts with in this case, two different versions of itself, delayed versions. In prolation canons, it's the same idea but at different speed. This means that a given melody interacts all the time with different parts of its original father melody that goes slower, for example. Right? So to make this sound well, even with two voices, is very difficult. By the way, the simplest way to obtain a prolation canon is to convert nested sequences into canons. So in an HSC example you've seen before, which was played sequentially before, first the first line, second, and so on. If you play them simultaneously, you're going to have a prolation canon where the same melody is played at different speeds. So it's repeated once in the first line, repeated 4 times in the second line, and so on. And now this begins to sound like something. So this is what it sounds like. I added the last chord, so just to close it. But anyway, you can see that this begins to sound like something, but it's still extremely simple example, namely Euclidean, and all the voices start together, etc. So now I want to say a little bit about how we calculate fractal dimension and try to go fast through this. So let's start with the idea that you have just two lines of music, and the motif is performed at time t1 and t2 in the 2 lines, and the number of repeats are R1 and R2. Right? These are the 2 basic parameters: how many times it's repeated and at what speed. Right? So a simple analog of the fractal dimension will tell you that the fractal dimension here is log of the number of copies, which now is a relative number of copies in line 2, number of copies in line 1, and the inverse of times there in the denominator. Right? For n voices, you just generalize it. And we put a 1 over n to exclude repeats. and this is what it looks like, where these n is the relative number of copies in line I relative to j, and you have scales and inverse scales that go into this definition. So this is what we call a temporal fractal dimension. It has lots of nice properties. For example, and by the way, it has to be in logs because hearing is logarithmic, and the distances between notes in a equally tempered scale in logarithms are equal, but not in frequencies. So you can invert the order of lines. That's good because it doesn't matter how they're written. If the voices are commensurate, that is to say they start and end together, include no rests, then this ratio that appears there under the sum is just 1, and you obtain temporal dimension, which is integer, so Euclidean situation. But you can have other cases. For example, for the HSC example you've seen before, well, that's just example of Euclidean 3 minus 1. For Cantor Set Projection Canon I showed you, this formula gives this, which is or is not Euclidean depending on whether n is even or not. Now I said that you have to include tonal complexity, the tonal characteristic of music, not just the length of the note, right? So this is how note frequencies are defined in equal temperament scale, so that the full harmonic scale has 12 notes and full octave, and the ratio of the first to the last is 2 in frequencies. And so we thought of the simplest way to measure this would be to measure the ratio of consecutive notes in logarithms, and there's an absolute value there to avoid negative numbers. And it should be normalized by note intervals for reasons I have no time to explain, but it's easy to guess. And so you get this tonal complexity character chi. And this also has some nice properties. It does depend on order of notes. The larger the pitch intervals, the larger chi, and so on. Some other things that are pretty obvious. And here's some examples. You have a set of equal notes, equal pitch. The kappa chi is 0. And as you get to more complex situation, that it increases. There are other possibilities of defining this chi, but I'm just going to show one here. And importantly, transpositions, inversion, retrogrades don't change kappa, right? So they're musically the same thing. And then we think of fractal dimension as made of 2 parts, the temporal and tonal part. And the tonal part derives from this chi parameter, and basically we treat it as a weight on the scale. This is really the simplest approach possible with the requirements that I've written there. So we multiply the scale by this character kappa, normalized kappa, and this results in this formula for the tonal dimension as written here. So one other nice property of this is that within 1 octave, dt, the tonal dimension index, is between 0 and the temporal one, d0, which means that the fractal dimension d, the sum of these two, must be between d0 and 2d0 within 1 octave. All right, so now to musical examples. How much time do I have left?
We should, till 3.
Till 3. All right. So I have a few examples. Let's see how many I can do. Correlation canons, as I say, are the main principal examples. So I've selected out of quite a few. We have 3 that span about 500 years, Josquin, Bach, and Shostakovich. And I'm including one nested sequence because it's a well-known piece by Holst. So you can see how that works. So let's start with Josquin de Près, who was a student of Ockeghem and really took this form, prolation canon, to its apogee. He was a mathematician and a musician, and overall a genius. And here is a portion of Agnus Dei from his well-known Mass, Missa Lomar Super Voces Musicales. And in here, the soprano line, the top line, goes through, it's very long, it doesn't repeat, it's just one repeat, but it's based on the 4 notes I've circled here, right? And you can see that they're repeated at lower speeds at lower speed in second line, and also lower speed in the third line. All right, so you can see the first 3 equal notes are here, 1, 2, 3, and then this note, it's a dotted note over there, which means longer, so this one is longer, and you have 1, 2, 3, 4, and so on. And in fact, the whole music is dependent on this seemingly very simple theme. This is a simplified notation. This is what it sounds like. And this is what it, so we've calculated various things here, and the dimensions are shown here. And one can also find effective scale. Anyway, the total dimension is about 2.6. Here's what it really sounds. This is what Josquin wrote. He wrote just one line, and you're going to see 3 markers move at these 3 different speeds through this music. Here are the speeds denoted in different colors. Maybe. So it's remarkable. It sounds wonderful, even though this is developing in 3 different speeds. This is so-called Goldberg canon. So on his copy of Goldberg variations, at the end, Bach wrote 14 canons by hand, and they were discovered not so long ago. And here's number 14. It looks like this. There are 4 lines, and basically the theme, it has a complicated structure, so I have no time to fully describe it, but the theme is in these 8 notes. This is in fact the Goldberg theme, and you can see the speeds here, and this is what it sounds. And here's our calculations of things for it. Total dimension about 3.7. And here's, I've just played the beginning of this because of time. Here's how it's written in contemporary notation. And you will see that it's made of the same material, but each line is played at different speeds, as shown here. And this, enough of this, but it continues for a little while, cycling through. Here is a nested sequence by Holst. This is from the planets, Uranus. And the theme is 4 notes. As you can see, the 3 dotted full notes, and double that for the last. And it's a little modified from what a perfect nested sequence would be, but otherwise it's pretty close. But this line we wrote in order to complete the second order. Here's what it sounds. Holst omitted this last line because it resolves the tension. And this whole piece is about building tension. I'll show you this. And here is an illustration of what it sounds like. And the sort of... first order, 4 notes. Second order, third order. And then nothing really happens, it's just building tension. The theme again, slow. Same speed. Slower. So you can see he's playing with this. I'm going to skip Shostakovich because I don't have time, and I'm going to go to key points. So for relation canons, where music unfolds together at different time scales, are sound analog of spatial fractals, we think. They entail formidable challenges, and are rare, so are real fractals. There are nested sequences, which is a form that mimics simultaneously occurring different scales. And from very simple rules, that's very typical of fractal structures, these progression canons develop in superbly complex and rich shifting tapestries. I didn't have a chance to play Shostakovich for you, which is really complicated. And this temporal fractal dimension reflects scaling regularity of motifs, but the full dimension must include tonal complexity. And more general remarks are that mathematics and music are bound together. That's Helmholtz's statement. Scaling regularities in music requires a great deal of skill and therefore are rare. They also require heightened attention from listeners. And lastly, they serve to convey perfection of form, inevitability of musical developments, because you anticipate what the various scales are going to go to. And I want to finish with this quote from Josquin when he was an old man. He said, "The overriding principle was that of harmony and proportion. The music had to be a reflection of the balanced order of God's universe." That's what he thought these fractal patterns do. Anyway, thank you very much.
Anybody have questions? Any questions? Yes, go ahead.
I'll start with going right back to the beginning. You said you wanted something which was more satisfying to you than the statistical approaches. So if you applied those statistical methods to what you talked about later in your talk, what information would you get that was different or inferior to your present?
Well, good question. I didn't actually do this calculation because I don't think it's very meaningful. Actually, none of these pieces, and another reason is that none of these pieces were analyzed as far as I know in existing literature. So I would have to do their calculation, which I didn't think was worthwhile. But yes, that's a good question.
Go ahead.
Yeah, so kind of the question that I'll talk about tomorrow, but so you considered fractal music. Is there such a thing as multifractal music? And have you considered that?
Yes, there is. So Occam wrote double fractal patterns. I have an example, but I just didn't have time for it. Where he has 4 voices, and the soprano and tenor have a relation, fractal relation, and then, soprano and alto, and then tenor and bass have. But the ratios are different. And these 2 unfold simultaneously. So it's a real feat of musical and mathematical prowess. But it's a little complicated to explain, so I removed it. So yes, the answer is yes, but it's very rare.
There was another question back here. Yeah, go ahead.
Very interesting, Professor. Fractal dimension not necessarily is complexity.
That's correct.
Have to consider measure complexity in another kind of music, not classical, because classical is obviously the perfect example for fractal dimension. But how about rock or jazz?
Yeah. So, two brief answers to this. Number one, people measure complexity in various ways. For example, using information theory. So there is a number of papers on that topic in compositions, almost always in classical music. But there's someone in Indian composition, Indian music also. And as for non-classical, I wanted to include example in our paper, and we looked for one. And somebody told me the group Genesis had an example, and I listened to it, and but it didn't really have the proper structure. It had a little canon there, very nice, but all voices, which were really 2 keyboards going at the same speed. So I didn't include it, not because I'm a complete snob, but it's a very complex form. It's not trivial to do, to make it sound good. So it's, if anybody knows of an example of music, popular music with it, I'd be very happy to hear about it. But I didn't find it.
So this kind of analysis is very structural in a way, right? So one of the questions that one might ask, is, can you make some argument about, cultural evolution, or how a genre evolves with this kind of measures?
Yeah.
Can you or cannot?
Yeah. So I don't know. We haven't done it yet. We're still at very early stages of developing this approach, and it has some places where it might be improved, which I didn't mention, but we're thinking of a slightly different way of measuring complexity, tonal complexity. And only when we're satisfied with this, you can just take it then and see how it applies, for example, to different styles of music and so on. So, but we haven't done this yet, and it's just been published. As far as I know, nobody has done it yet. But the statistical methods have been applied with various results to a broad range of examples.
Would you say that, okay, I'm not saying we should necessarily dismiss all statistical methods. Say, maybe you could use the statistical method so it can capture the special cases that your method seems to capture. I don't know, maybe delay embeddings and things like this might possibly, some of the dynamical systems literature sort of says, okay, you take this time, this window, and then you delay it, and then you look at the geometry of these embeddings, and you see something emerge from that. I'm wondering if that might capture some of the fractal structures, or fractal structures that are less obvious, or not as, say, there is a kind of fainter fractal structure in other pieces, say from classical music, that don't obviously have, but have some of the structure there. So I think signatures of it that are there.
Yeah, so I don't dismiss statistical approaches, but they are not capable of, they are capable of, what they really provide is self-correlation. They are a measure of self-correlation in a composition between different parts. So, like Hurst exponent or the affine correlation. And they're incapable of registering self-similarity. So to the degree that you let go of the requirement that there's actual self-similarity, meaning you have a theme that is sounded simultaneously at different speed, which must be the case if you take it seriously as a fractal pattern. These statistical methods are not capable of distinguishing between something that is or is not. But perhaps they provide some information about the pieces of music. And there's a vast literature on this. We haven't started to compare our results with those things.
Okay, it is tea time, and I'm not going to cut into that. So any further questions have to happen there. Let's thank Andrzej very much.